back, student. Now today we'll discuss on stagnation properties, which is the topic actually in the course in your compressible fluid flow, okay, in applied thermodynamics. Now first question is that what is stagnation properties? Okay, stagnation property or point is particularly a point, as the name suggests, that it's basically is it in rest condition, or is it is basically in a particular point or state. It defines a particular point or state in a flow field. As you know that the fluid is basically two types depending on the density changes, or depending on the density. If it is depend on the density, then it is sometimes it is called incompressible or compressible type of fluid flow. Now today we'll discuss on stagnation properties. Okay, stagnation properties or point is particular a point in which a flow field where the total local velocity of the fluid is zero. Obviously, if you suppose there is one duct there, if the fluid is flowing through a particular pipe or particular channel, then after some time, that if it resists with some object, obviously at that particular point or some surfaces, at outer surfaces, the velocity of the fluid will be zero. Now at that particular point, that point exists at the surface of object in the flow field where the fluid is brought to rest by the object, and this is the reference state in a compressible fluid flow and designated with subscript 0. So basically stagnation properties are basically thermodynamical properties, basically which defined or which define basically a thermodynamic property or fluid properties, okay, in which it defines the parameters, the state of a particular fluid system, that basically its pressure, temperature, its density of that particular fluid, what is the change, what is the value of that. Now that is basically defined as stagnation property. Okay, now this is the reference state in which the compressible fluid flow and designate with subscript 0. That means stagnation properties may be pressure, may be temperature, may be density, may be volume, in terms of, but stagnation properties basically, as you know, the pressure, density, volume, and any other thermodynamic properties and fluid properties also designate P, T, V, like that. But in terms of stagnation, when it transforms into stagnation properties, which is basically a point or state in a flow field where the local velocity of the fluid is 0, at that particular point the pressure, temperature, volume, that will be designated by P0, T0 and V0, like that. Okay, that's why it is written as designated with subscript 0. Now let us consider a steady flow open system. Now let us consider this. As you know that it's a steady flow open system from the first law of thermodynamics in your chapter, that in first law of thermodynamics applied to the flow process, in which you already go through the steady flow energy equation. Okay, now here we consider that a steady flow open system here, and it's a basically condition is that perfectly insulated. That means there is no heat transfer takes place. Perfectly insulated means there is no heat transfer takes place from surrounding to system or system to surrounding. Insulated duct basically a pipe like that, a system in which the fluid is flowed, that system is called basically duct, in which the gas flows with no sap work. We assume that there is no sap work involvement are there. Okay, only and one more important assumption is that flow is frictionless. So there is no friction between the fluid within the fluid. So there is no friction, so that it's basically the process is reversible adiabatic. Okay, so that the process is basically reversible adiabatic condition we can obtain from that, because to obtain the reversible adiabatic or isentropic compression or isentropic process obtained, the condition is such that so there will be no friction at all, and as it is adiabatic process, there is no heat transfer takes place. Okay, so all these assumption will follow that, so that the reversible adiabatic condition are obtained. Okay, now consider a single stream. Okay, now consider a single stream Now consider a single stream of fluid entering and a single stream of fluid leaving the control volume. Okay, as we know that the steady flow energy equation, when a single stream entering and a single stream fluid leaving the control volume, the expression was that Q plus M into H plus V1 square by 2 plus GZ1 is equal to M into H2 plus V2 square by 2 plus GZ2 plus W, in which Q is the heat transfer, M is the mass flow rate, H is the enthalpy, V is the kinetic energy, or velocity is basically V1 square by 2 is indicating your kinetic energy, and GZ1 is your datum head or basically potential energy it indicates, where G is the gravitational constant and Z1 is the datum head from your reference line, and M is also mass flow rate, and H2 is your enthalpy at exit section, kinetic energy at exit section, and potential energy at exit section, and W is your shaft torque. So this is the general steady flow energy equation, in which one single stream entering and one single stream of fluid entering and single stream of fluid leaving the control volume. Okay, now we already gone through this in your previous semester. Now, as you know that, as we assumption that that there is no heat transfer takes place as the process is reversible adiabatic, so Q will be equal to 0, and we already assumed that there is no shaft torque involved, so W is equal to 0, and as you know that Z1 is equal to Z2 when if the fluid is flow through a particular duct on a flow 5, so obviously the height of the fluid flow from the reference line will be same, so Z1 is equal to Z2. Now if you assume on all of these criteria, then the equation becomes H1 plus V1 square, so Q is equal to 0, M both are same, and V1 square Z1 is equal to Z2, so that's why GZ1 and GZ2 will be cancelled and W is equal to 0. After all, the expression will be H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. Now summation of what you see that summation of now we consider, as you know, this up to it's okay, I think. Okay, sorry. Now summation of enthalpy plus kinetic energy remains constant under reversible. What you see that summation of enthalpy plus kinetic energy remains constant under reversible adiabatic conditions. We assumption on that that Q is equal to 0 and W is equal to 0 and Z1 is equal to Z2, so that in the particular conditions, what you see here that summation of enthalpy and kinetic energy remains constant, so H1 plus V1 square by 2 is equal to H2 plus V2 square by 2 under reversible adiabatic conditions in the absence of shaft torque, because W is equal to 0, and heat transfer also because Q is equal to 0. Now stagnation enthalpy or total head enthalpy, that is equal to, or isentropic enthalpy, stagnation enthalpy, okay, isentropic stagnation enthalpy or total head enthalpy can also define that H0, that is a stagnation enthalpy, okay, stagnation enthalpy is equal to H plus V square by 2. H0 is equal to H plus V square by 2, where H0 is your stagnation enthalpy and H is your static enthalpy. Okay, now from the basic engineering thermodynamics, I think all of you know that H is equal to Cp into T, so H0 will be Cp into T0, where T0 is the stagnation temperature, right? Now H0 minus H, that will be Cp into T0 minus T1 from that concept also, right? Now suppose what do you like that this is your HS diagram, in which what you see here that is the static pressure line, this is the isentropic stagnation pressure line, in which that indicates here that in isentropic stagnation pressure line, so this is the HS diagram, so that point if it is H0, so H0 will be, if it is H, so this is the reference line, so H plus V square by 2, this one is equal to H0, which already written in the previous lecture. Okay, so H0 is equal to H plus V square by 2. Now from the previous knowledge, the Cp into, as you know that, H0 is equal to H plus V square by 2, right? And H0 minus H is equal to V square by 2. So H0 minus H is equal to Cp into T0 minus T0, T, where T0 is stagnation temperature, T is your static temperature, is equal to V square by 2, which is the velocity, right? Now Cp by T will be common here, so Cp into T into T0 by T minus 1 will be V square by 2. So T0 by T will be 1 plus this one, so T0 by T is equal to 1 plus V square by 2 into Cpt, right? Now as you know that Cp and Cv, the value of Cp we can also from the basic engineering thermodynamics, Cp is equal to gamma R by gamma minus 1, right? Now in terms of here Cp, you just write down Cp is equal to gamma R by gamma minus 1, so that will be gamma R here, gamma minus 1 from here, so write down plus V square in T. Okay, just put down here Cp is equal to gamma R divided by gamma minus 1 here. Okay, now after all T0 by T is equal to, after all as you know that Mach number, already discussed that. Okay, now as you know that Mach number is the velocity of fluid divided by velocity of sound. Okay, is equal to, as you know that M is equal to V by C, and for reversible adiabatic process C is equal to, already proved that C is equal to gamma T, right? So in terms of C here you can write down gamma T. If it is square, so M, it will be M square is equal to V square divided by gamma T. So M square is equal to V square divided by gamma T. Now here it is V square gamma T. In terms of that, V square divided by gamma T, you can write down here gamma, right? So it will be T0 by T will be 1 plus gamma minus 1 by 2, and this one will be your M square from here. So the relationship between the stagnation properties or stagnation temperature with the Mach number will be T0 by T, very important relationship. T0 by T is equal to 1 plus gamma minus 1 by 2 into M square, where T0 is stagnation temperature and T is your static temperature, M is your Mach number. Okay, so this is the relationship between T0 by T is equal to 1 plus gamma minus 1 by 2 into M square. And now if you calculate the stagnation pressure, so stagnation, how do you calculate the stagnation pressure? It also same actually, that stagnation pressure is defined as the pressure which would be obtained if a flowing gas is in a duct is brought to be rest in reversible adiabatically process. So stagnation pressure, or you can say that isentropic stagnation pressure, both are actually same, but we just consider here when the fluid is flow on a particular duct or channel, that is basically condition of reversible adiabatic conditions. So as you know that for reversible adiabatic process, the relationship between is that P0 by P or P2 by P1, like that. We are actually familiar with that. P2 by P1 is equal to T2 by T1 to the power gamma minus 1 by gamma. So in terms of P2 by P1 by is equal to, you can write down also gamma divided by gamma minus 1 from that concept. Now as you know that T0 by T, so T0 by T is equal to 1 plus gamma minus 1 by 2 into M square. So in terms of that, in which P0 is your stagnation pressure and P is your static pressure. So P0 by P is equal to this one. So in terms of T0 by T, already proved that T0 by T is equal to 1 plus gamma minus 1 by 2 into M square. Okay, so in terms of that, you can write down T0 by T is equal to 1 plus gamma minus 1 by 2 into M square from here, from these equations. Okay, and this will be same, gamma divided by gamma minus 1. So similarly, you can also write down also for in terms of density, for stagnation density, rho 0 by rho will be same. You can try yourself, that will be 1 plus gamma minus 1 by 2 into M square to the power 1 by gamma minus 1. So this is the class for stagnation properties. Okay, I think all of you clear of that particular topic. Okay, thank you very much for listening me and watching me, and goodbye.